From hoverboards to flying cars to cloud cities, anti-gravity is a staple of science fiction and of our dream of a less earthbound future. But in the real universe, gravity appears to be a purely attractive force. Feels like its main MO is keeping us stuck on the surface of this lonely rock. But maybe, if we science hard enough, we can remove the fiction from science fiction. So, for the sake of our flying cars, we should at least try. And for many years, physicists have wondered whether a certain well-known exotic material may experience gravitational repulsion from the Earth. That material is antimatter. And physicists at CERN have just completed a very long and very difficult experiment to answer a seemingly simple question. Does antimatter fall down, or does it fall up? Antimatter, the evil twin of regular matter. Or is it just the misunderstood twin of regular matter? We've made it in labs and seen that an antimatter particle has the charge and other quantum properties that are opposite compared to its regular matter counterpart. The only thing that's the same is its mass. Except, it may be that in at least one sense its mass may be different, even opposite to regular matter. And that fact may give us our anti-gravity, or at least teach us profound truths about the nature of reality. The trick is going to be to think about mass not as one property of an object, but rather as two distinct and independent properties. There's inertial mass, the resistance to being shoved or slowed, and there's gravitational mass, which determines the heft of your gravitational field, and your response to other such fields. Now, we've explored an aspect of this idea previously, and this is a good review episode for the studious, or a good follow-up episode for the impatient. Today, we're going to focus on the antimatter and the flying car implications of splitting inertial and gravitational mass. Let's start with Isaac Newton's description of all of this. We'll move to Einstein's upgrade later. Inertial mass is the mass in Newton's second law. It determines how much force you need to apply to achieve a given acceleration. On the other hand, gravitational mass is the mass in Newton's law of universal gravitation. It acts as the gravitational charge, determining the strength of the gravitational field and the strength of response to another such field. We almost always assume that inertial mass and gravitational mass are the same thing. This equivalence is called the equivalence principle. We normally think of the equivalence principle as being the epiphany that led Einstein to the general theory of relativity, but it's older than that. So, 100 years ago, Einstein realized that there should be no experiment that could distinguish between the feeling of weight you have when supported in a gravitational field and the same feeling when being accelerated at the correct rate in empty space. This statement of the equivalence principle requires that inertial mass, the mass resisting acceleration, is the same as gravitational mass, the mass that responds to a gravitational field. But over 300 years prior to Einstein, this guy named Galileo demonstrated the same thing when he dropped a pair of balls off the top of the Tower of Pisa. They had different weights but the same size, so their air resistance was equal. He found that they reached the ground at the same time. We've now done this experiment in the near vacuum of the moon's surface with a hammer and a feather, giving the same result. Around a century after Galileo's Pisa drop, Newton came along and figured out the equations that tell us why. Let's say that the gravitational mass in Newton's gravity law is the same as the inertial mass in his second law of mechanics. Then, when we calculate the acceleration experienced by a massive object in a gravitational field, these two masses cancel out. In other words, more massive objects feel a stronger pull, but are also harder to accelerate. Because of this, hammers and feathers fall at the same rate on the moon. Gravity is always attractive, because gravitational charge, aka mass, is always positive, compared to electromagnetism, which can be attractive or repulsive due to electric charge being positive or negative. So, what happens if we allow mass to be positive or negative? We covered the details in our previous video, but long story short is that two positive masses behave as normal, two negative masses repel each other, and a positive mass is repelled by a negative mass, while the negative mass is attracted to the positive. That last part means positive and negative mass would chase each other, accelerating at a constant rate forever. That breaks conservation of momentum and energy and so can't be right. The thing that really breaks physics in this scenario is that we allow negative inertial mass, which will always move in the wrong direction to an applied force. But perhaps we can fix this by separating our mass types. What if inertial mass is always positive, but gravitational mass can be positive or negative? Then, a pair of positive and negative gravitational masses will mutually repel each other, which is just what we want for anti-gravity. But if we say that inertial and gravitational mass are not equivalent, then we've overturned the equivalence principle. We should not do that lightly. After all, it's one of the founding axioms of general relativity, which is itself an insanely successful theory. But it turns out that for the type of repulsive gravity that we're looking for, we have to break the equivalence principle. Speaking of general relativity, let's see how negative masses work here. In GR, gravity is explained as mass causing the fabric of space and time to curve so that things move differently due to that curvature. In the classic rubber sheet analogy, objects with positive mass depress the sheet, causing straight lines to deflect towards them. Hypothetical negative gravitational masses would be depicted by pinching the sheet upwards, causing straight lines to move away. This picture makes it somewhat intuitive why the motion of particles seems to only depend on the shape of the gravitational field, which itself depends only on the gravitational mass of the central object. Objects follow geodesics, the straightest lines in curved space regardless of their own mass. In fact, we can also think of this as the gravitational and inertial masses cancelling out, just like with Newtonian gravity. We can see that cancelling in something called the geodesic equation, which is the equation of motion for a particle in general relativity. Normally, the mass of the moving object doesn't appear in this equation, just like it doesn't in the Newtonian acceleration equation. But it's actually hidden. If we separate inertial and gravitational masses, we see it here. And the geodesic equation also tells us how positive and negative gravitational masses interact. We're going to keep inertial mass positive because anything else is insane. Now, negative gravitational masses change the sign of the gravitational field or the sign of the mass of the interacting particle, or both. If both masses are positive or both negative, the minus signs get cancelled and we have regular gravitational attraction. But if only one of those masses is negative, then we end up with a new minus sign between the field and the object. The effect is gravitational repulsion. In other words, something with a negative gravitational mass would fall upwards in Earth's gravitational field. Okay, great. So, to make an anti-gravity engine, we just need a negative gravitational mass. So, what's all this about antimatter possibly having this property? An antimatter particle has the same mass as its regular matter counterpart, but is opposite in many quantum properties. And that doesn't sound helpful. If antimatter has the same mass as regular matter, then where's our negative mass? Well, remember, we just broke the equivalence principle, at least in our imaginations. So maybe antimatter can have positive inertial mass but negative gravitational mass. Two reasons we might think this is the case. First, based on its response to the electromagnetic field, we know that antimatter does have positive inertial mass, but we've never actually measured its gravitational mass. Well, actually, just recently we finally did, and I'll tell you the results in a bit. But we've had a lot of years to come up with reason 2, that there are theoretical motivations for thinking that maybe antimatter has negative gravitational mass. To understand this, we need to understand the theory behind antimatter a bit better. Antimatter is what you get when you take regular matter and do 3 things to it. Flip its charge, reflect its spatial coordinates, so clockwise particles become counterclockwise, and reverse its time axis, which is equivalent to reversing all of its motion vectors. These transformations are called charge conjugation, parity inversion, and time reversal, and applied together we have a CPT transformation. CPT transform regular matter, and it becomes antimatter. And of course, there's a homework episode for you on this topic. Most physicists think that our universe has to be CPT symmetric, which means that although the laws of physics change if you perform any of these transformations separately, if you perform all 3 together, the laws of physics should look exactly the same. CPT transform the whole universe, and you get an antimatter universe that follows exactly the same laws of physics as our regular matter universe. But there's at least one big reason to wonder if CPT symmetry is broken, and that's because almost all of the matter in the universe is regular matter with hardly any antimatter. In a perfectly CPT symmetric universe, matter and antimatter probably should have been created in equal quantities soon after the Big Bang. If we found out that CPT symmetry is broken, and how it breaks, we could perhaps solve this big mystery. But I digress. We are here to build a flying car. And understanding the CPT symmetry can help us do that. If this symmetry is true, then all the laws of physics should look the same under CPT transformation. So, an antimatter universe should run by the same equations, including the equations of general relativity. And indeed, if you apply a CPT transformation to the geodesic equation, you get some minus signs as you reverse the flow of time and flip the dimensions of space, etc., but they cancel out and give you exactly the same equation you started with. That's equivalent to switching both of a pair of mutually gravitating objects into antimatter. They'd still attract each other. In fact, we can't even say if they both have positive or negative mass. The math looks the same as long as they have the same sign of mass. General relativity in general seems to be CPT invariant. But what happens if you CPT transform only part of the equation, if you turn one of a pair of masses into antimatter? The exact way a CPT transformation interacts with GR is still being debated, but at least some physicists have argued that the result on the geodesic equation is to introduce a minus sign, either to the field or to the mass in motion, depending on which you turn into antimatter. But mathematically, that's equivalent to changing one of the gravitational masses negative. So, some ways of thinking about the symmetry of general relativity gives antimatter negative gravitational mass. Remember that this is a contested interpretation, but the result would be gravitational repulsion and hoverboards. At the very least, it's definitely worth finding out whether antimatter falls up or down, whether for the awesomeness of our vehicular future or just to see if there's any weirdness in the gravitational interaction of antimatter that could poke holes in CPT symmetry and help us answer some very big questions. So, let's get to the experiment, finally. What happens when you drop an apple made of antimatter? And to start with, why is it so hard to even do this experiment? Well, it's because we don't have any antimatter apples. Antimatter is extremely hard to create and to keep contained. It instantly annihilates when it encounters regular matter. At best, we have antimatter atoms. The difficulty is also due to the fact that the gravitational force is so weak compared to the other fundamental forces. For example, if we wanted to measure the effects of gravity on a free-falling electron in the Earth's gravitational field, it would be like trying to measure the force of gravity that a human body exerts on a feather. No, not that astronaut's body on the dropped feather, but the force that your body here on Earth exerts on that feather on the moon. Add the fact that any antiparticle we analyze will be subject to vastly greater forces from ambient electromagnetic fields, and this becomes an intensely difficult experiment, but not an impossible one. So this is a CERN experiment that has been years in the making. It starts with the antimatter production line by the Alpha collaboration. This team has managed to create and magnetically trap hundreds of stable anti-hydrogens, consisting of a positron orbiting an antiproton. Their sister collaboration, Alpha G, then takes these atoms and drops them in freefall in a vacuum chamber. That sounds simple, but it's an extremely delicate operation. Because of the extreme smallness of the gravitational force on these atoms and the other effects that jostle them around, they don't all just tinkle downwards. Some move up, some move down, and at different rates. But by measuring the rate and timing of anti-hydrogen atoms that reach both the top and the bottom of the chamber compared to regular hydrogen, the relative gravitational acceleration on the atoms can be calculated. And after the first run of the Alpha G experiment, it turns out that acceleration is downwards. Yep, they're almost certainly not falling up, and that likely dashes our hopes for repulsive gravity from antimatter. However, there is tentative evidence for something interesting. The gravitational force may be slightly weaker on these anti-hydrogen atoms compared to regular hydrogen. This fairly preliminary data suggests that the gravitational acceleration on the anti-hydrogen is 0.75 plus or minus 0.13 times that of regular hydrogen atoms, meaning antimatter might fall a bit slower. That actually sounds like a big difference, but it's less than a 3 sigma result, so it could be a fluke. In fact, the scientists of the Alpha G paper do claim that the gravitational acceleration of antimatter is consistent with it being the same as regular matter. And that's because misleading sub-3 sigma results happen all the time. And when it's something really unexpected like this, it's much more likely to be a statistical fluke. Remember, we're dealing with only hundreds of atoms here, so random variation is going to be significant. That said, if there is a difference in the gravitational force felt by matter versus antimatter, it would be extremely exciting. It would mean a violation of CPT symmetry. It would mean the universe treats antimatter differently to regular matter, perhaps explaining why there's this enormous imbalance between the quantities of each. Alpha will continue to build anti-hydrogen atoms, and alpha G will continue to drop them, and they will fall down, but whether they fall at the same rate as regular hydrogen will be known with increasing confidence over the next few years. So we may not have a clear path to our levitating cars, at least yet, but we do have a path to either solidifying or breaking CPT symmetry, and so understanding what's currently the most fundamental symmetry in spacetime. We're told there are 4 fundamental forces: the strong and weak nuclear forces, electromagnetism, and gravity. Except maybe gravity is actually no more fundamental than, say, the force of a stretched elastic band. Maybe gravity is just an entropic byproduct, an emergent effect of the universe's tendency to disorder. So, if you allow that entropy to hold you in your seat for a bit, I'll tell you all about it. Gravity is the odd one out among the fundamental forces. It's enormously weaker than the other 3, and it's also not a quantum force. At least it's not, in general relativity, our best description of gravity. And gravity has steadfastly resisted our century-long effort to quantize it, to unify it with the other fundamental forces. But what if that's because gravity isn't quantum? In fact, what if it's because gravity isn't even fundamental? There are a number of proposals along this line, including the buzzy recent work by Jonathan Oppenheim, but we're going to have to come back to that, because there's an idea that you've been asking us to cover for years now. That's the emergent entropic gravity of Dutch physicist Erik Verlinde, who tells us that it's not some fundamental force or the curvature of spacetime that's keeping you in your chair right now, but rather the rise of entropy on the boundary of the universe. Today, we're going to lay out the basics of Verlinde's entropic gravity as it was published back in 2010. We'll follow up with an episode on the evidence and the criticism and what the idea has to say about dark matter and dark energy. This episode follows directly from our last one, where we explored how space can emerge as an inward projection from its infinitely distant boundary through the holographic principle. A lot of what we talk about today will draw from that episode, so it might not be a bad idea to check it out. But let me recap anyway to emphasize the most important stuff. I'm also going to sprinkle in a bit of math, and we'll use that to construct Verlinde's ideas. But if the math isn't your cup of tea, relax. I'll give you everything that you need to follow with normal human words. So, the holographic principle grew out of black hole thermodynamics, from the fact that the information that can fit inside a black hole is proportional to its surface area. That information is hidden from the outside world, so this also gives the black hole an entropy, given by the Bekenstein-Hawking formula. It turns out that the same information limit applies to all of space, so that it's in principle possible to encode the contents of a universe on its boundary. In fact, according to the holographic principle, the particles and fields and gravity and laws of physics that govern our universe also play out in lockstep on its infinitely distant but infinitely compacted boundary. On that lower dimensional gravity-free boundary, a very different set of laws encode everything that happens on the interior. The boundary encodes what we call the bulk, and perhaps vice versa. The only concrete mechanism for this that's currently known is Juan Maldacena's ADS-CFT correspondence, which unfortunately doesn't quite apply to our universe. Still, it's a strong lead that there is a version which does. In ADS-CFT, the interior space, the bulk, contains a string theory, and gravity emerges within that string theory. But we don't need string theory to see how gravity might be a natural prediction of the holographic principle. Last episode, I showed you a scheme by which this extra dimension can be encoded in the scale of structures on the boundary, with larger structures on the boundary manifesting as structures closer to the centre of the bulk. Today, we're going to explore one idea for how gravity can also emerge within that space as a statistical side effect of the interplay of whatever it is that's happening out there on the boundary. This is the entropic gravity of Eric Verlinde. Now, entropic gravity is by no means broadly accepted, but it is taken seriously by reasonable physicists. After all, there is a fascinating and still mysterious connection between gravity and entropy, as Bekenstein and Hawking discovered. And there's a fascinating neatness to Verlinde's idea that seems like it's telling us something, even if it isn't the whole picture, and maybe even if it's wrong. To understand how gravity might arise entropically, let's think about a less out there system. We'll use the same thought experiment that Verlinde uses in his entropic gravity paper. Imagine a long molecule that is free to move and fold in any direction. We place it in a box of constant temperature with one end fixed to the wall of the box. If we ignore any possible external forces acting on the molecule, we might expect it to just curl up. This is because of all the ways the molecule could move, it's far more likely to end up in a coiled configuration than remain straight. This is one way to think about entropy. The molecule will almost always take a more probable, higher entropy configuration of being curled up because there are way more configurations, or what we call microstates, in which the molecule is curled compared to it being straight. Being in one of the many random coiled states is a higher entropy configuration than the very few straight states. If we straighten the molecule, we have to exert a force and expend some energy to do so. If we let go, it'll curl up again because there's an effective force pulling it back. I should add that there's nothing magical going on here. The molecule shares its temperature with the air in the box, the atoms have randomly oriented vibrations and are being randomly smacked by air molecules, and these will pull and push the molecule towards random configurations, which are overwhelmingly the coiled ones. There's a simple relationship between the force required to pull the molecule or the entropic force that the molecule exerts on you. This is really saying that the amount of energy, the force times the distance pulled, is equal to the temperature of the system times the change in entropy after that little motion happens. Or that the force is equal to the temperature times the entropy gradient. And we call this an entropic force. It's exactly what you experience when you pull on an elastic band. In fact, any time you have the movement of matter in the service of increasing entropy, there's an entropic force. For example, if you force all the air in a room into a box and then release it, it'll rush to fill the room and generate an enormous entropic force in doing so. The proposal of Eric Verlinde is that gravity is also an entropic force. At first glance, that seems odd. Gravity is a property of spacetime itself, even empty spacetime, so what exactly is pushing or pulling in empty space? Verlinde constructs his argument in the context of a holographic universe, in which at least one dimension of space is also emergent. He argues that the entropy of the stuff on the holographic boundary must increase, and that rising entropy manifests as gravity in the interior. To build up this idea, we're going to need to keep in mind dual pictures. Something is happening on the boundary, and something is happening in the bulk, and they encode the same thing, even if they sit very differently in our mental imagery. We'll flip between them as convenient, and even merge them slightly. But remember that these are two distinct ways of describing the same system. Okay, so somewhere in the bulk of a holographic universe we have a star with some mass. Let's see if we can figure out the gravitational force produced by the star without ever using any theory of gravity, just by visiting the boundary. To derive such a law, we want to know how much gravitational force is felt at different distances. So let's imagine a series of spherical surfaces around the star. If the star is massive and compact enough, then one of these surfaces would be an event horizon and we'd actually have a black hole. Then the entropy of that surface would be the Bekenstein-Hawking entropy. Basically, it would represent the amount of information of everything that previously fell through that surface. But even if this surface isn't an event horizon, we can give it an entropy. It's also the entropy of everything interior to that surface. But that makes the most sense if we zip out to the boundary. If this is a holographic universe, then the particles on this surface map to the boundary. In fact, the particles on surfaces of all sizes map to the same boundary and play out together, overlapping in that lower dimensional space. We want the entropy of this one surface with respect to someone outside that surface. That translates to how much information is hidden within that surface. Let's start with the holographic boundary from which our bulk universe emerges. Imagine that it emerges from the outside in. Now that's not really the case, but it helps us represent this visually. We're going to partially emerge our universe down to this one surface, so we can depict a special subset of the boundary as actually lying on this surface in the bulk. This is the part of the boundary that corresponds to everything below this surface. So from now on, when I say boundary, I mean the component of the holographic boundary corresponding to the region of the bulk enclosed by this surface. Okay, hold on for just a little bit of math. We know that this surface contains a mass, so we can say that it also contains energy by Einstein's E equals mc squared. That's the energy of the interior, but it also has to be the energy of the corresponding holographic boundary. We can also give that boundary a temperature, assuming the stuff on the boundary is in thermal equilibrium so that that energy is evenly spread over all possible states. And that n thing is just the number of possible states on the boundary and the total number of arrangements of particles inside the volume that would give you the particular values of energy, mass, and temperature. But that also corresponds to the amount of hidden information within the surface, its entropy. We know the maximum value for this. It's the Bekenstein-Hawking entropy, so the number of Planck-length squares over that surface. For our surface, let's just assume that the entropy and n are still proportional to the surface area, but presumably smaller than for a black hole. Okay, one more step. We want the gravitational force, so we need another particle to feel that force. Let's add a tiny mass and move it close to the surface from the above emerged part of space. When that happens, the entropy of the boundary increases because the information from that object is lost to the external region. The boundary gains the same amount of entropy as dropping something into a black hole event horizon. This equation is just saying that the surface gains minimal entropy, equivalent roughly to a bit when the particle merges with the surface, which we define as it getting within its own quantum wavelength, in this case the Compton wavelength of the surface. But just like we saw with the coiling molecule, this tiny increase in entropy should have a corresponding entropic force. Whatever crazy interactions are happening out there on the boundary, they are statistically inclined to bring our particle closer to this surface because that motion increases entropy. If we bring everything together, the delta S over delta X from dropping a particle through the horizon, and the temperature from the overall entropy of the surface, all the H bars and the C's and the KB's cancel out, and we replace the area of the sphere with 4 times pi times its radius squared, and we see that the algebra shakes down to Newton's universal law of gravitation within some constant. And if that constant is 1, because we got our surface entropy formula right, then we have Newton's exact equation. We just derived Newtonian gravity with arguments that are entirely thermodynamic. This is basically saying that if objects in the bulk move in such a way as to maximize entropy on the boundary, then that motion means falling towards other masses in the bulk. Remember that Hawking and Bekenstein used gravitational theory and quantum mechanics to get black hole thermodynamics. But entropic gravity turns this on its head. It starts with thermodynamics and finds that gravity just falls out. But let's not get ahead of ourselves. Firstly, this is just Newtonian gravity. Can entropic gravity reproduce Einstein's general relativity? Well, in the 2010 paper, Verlinde argues that yes, it can, although the derivation is a bit much for this episode. In 2016, He also published another paper that argued that dark matter can be explained by this idea and that it's connected to dark energy, although this requires some extra assumptions. And speaking of assumptions, the validity of this whole idea rests on the validity of the founding assumptions. Not least of those is the requirement of a holographic dual to the gravitational universe. And unless we can find a version of ADS-CFT that works for our universe, this feels like a big if. The debate over entropically emergent gravity is real, and is taken very seriously by serious physicists. That means it's worth doing another episode to pick this apart. But in the meantime, this has been pretty hard work, so let's just have a little lie down. I mean, can we really be expected to fight the rising entropy at the infinite boundary of our holographic space-time? The holy grail of theoretical physics is to find the long-sought theory of quantum gravity. But what if this theory is as mythical as that grail of legend? What if gravity isn't weirdly quantum at all, but rather just a bit messy or random? So says the post-quantum gravity hypothesis of Jonathan Oppenheim. We have two great theories in physics that together appear to explain almost everything. There's general relativity, the theory of space and time and gravity, and the larger scales of the universe. And there's quantum mechanics, the theory of atoms, matter, and the smaller scales. These theories are each verified to astonishing precision, and yet seem to contradict each other at the most fundamental level. We've talked about these conflicts in the past, and the efforts to resolve them by unifying quantum mechanics and general relativity into a single theory. We usually think of this master theory as quantum gravity, but that name hides an assumption. The assumption that the solution is to quantize gravity in order to work correctly alongside quantum mechanics. But after nearly 100 years of very smart people thinking about this, we still don't know how to make gravity quantum. Well, what if we've been going about it wrong all along? What if gravity simply isn't quantum? Today, we will ask whether it's possible to come up with a classical theory of gravity which is compatible with all the weirdness of quantum mechanics. And according to physicist Jonathan Oppenheim, the answer is basically yes. But some additional weirdness must be added to gravity and its interactions. It must be random. Before we get into the type of randomness that gravity needs to make such a theory work, let's discuss what happens when one naively tries to couple classical gravity, as we know it, to quantum theory. Our starting point is Einstein's famous equations of general relativity. Here we have the Einstein field equations. We have the Einstein tensor, which describes the geometry of spacetime, equaling a bunch of constants, times the stress-energy tensor, which describes the matter and energy inside that spacetime. By the way, the Einstein field equations are pluralized because these tensors are multi-part objects. It's really a set of 10 partial differential equations. But despite the name, it's okay to think of this as a single equation. It equates the geometry of spacetime with its contents. As John Archibald Wheeler put it, space tells matter how to move, matter tells space how to curve. So let's just call it the Einstein equation. The Einstein equation is a classical equation. Despite being complicated, its parts are regular numbers and vectors. For example, the stress-energy tensor has things like momentum, energy, and mass for the objects inside the universe. Well, the Einstein tensor describes a smoothly varying field with a well-defined and singular value everywhere. The Einstein equation of general relativity describes spacetime and gravity, while the rest of physics is described by quantum mechanics, represented by the Schrödinger equation. The Schrödinger equation is distinctly not classical. It does not describe precise properties of objects, but rather tracks the evolution of the wave function, the fuzzy distribution of probabilities, representing what might be observed when a measurement is made. The subjects of the Schrödinger equation, like systems of quantum particles or quantum fields, are quantized. in that they tend to jump between discrete states rather than move or vary smoothly like a classical object or field would. We tend to think that our classical macroscopic world arises as the combination of countless quantum interactions. We say that the classical behavior is a statistical limit of large numbers of quantum interactions. In that spirit, many physicists believe that general relativity and the Einstein equation are not fundamental, but rather emerge from quantum foundations. And that's understandable because we know that matter and energy are fundamentally quantum. There must therefore be quantum fields and quantum particles that somehow work together to produce the classical stress-energy tensor. Those quantum entities do all the weird quantum stuff, like existing in superpositions or being in multiple states at once and having discrete energy levels. So, the classical stress-energy tensor on the right of the Einstein equation should emerge from some quantum analog. Standard approaches to unifying quantum mechanics and general relativity have tried to make the left side of the equation quantum also, effectively to find a quantum version of the Einstein tensor representing a quantum space-time geometry. But our long difficulty in making that work is what led Jonathan Oppenheim to ask, what if only the right side of the Einstein equation is quantum, but not the left? What if matter and energy can be quantum, but the space-time they live in is really fundamentally classical? The challenge here is that both sides of the Einstein equation have to be the same type of mathematical object. So if the space-time represented by the Einstein tensor is classical, then we should probably understand how a classical distribution of mass and energy defined by a classical stress-energy tensor can arise from quantum parts. Take the Earth, for example. Each of our planet's countless atoms has a bit of quantum uncertainty in its position. Each atom is in a superposition of being in multiple places at once until measured. If you were to measure one atom, its location would resolve randomly within a small range defined by the uncertainty principle. But each different possible location for that one atom gives a different stress-energy tensor for that atom, and so a different space-time geometry due to the gravitational field of the atom. So what if you try to measure the position of the entire Earth by finding, let's say, its center of mass? Think of that as measuring the position of every single atom in unison. If those positions all get defined randomly, then any significant variations cancel out. It's like flipping a coin a cajillion times. You tend to roughly end up with equal numbers of heads versus tails. In the same way, each time you measure the center of mass of the Earth, you'll get the same position, accounting for its own movement, of course. You find also the same stress-energy tensor, and so the same gravitational field each time you look. This is why the stress-energy tensor for macroscopic objects can be treated as classical. But what about describing the classical gravitational field for a truly quantum object? Let's look at two options. We can either write down all the possible stress-energy tensors for all possible locations of that object. The Einstein equation could then be used to find a whole family of possible gravitational fields for each of those. A superposition of many mass-energy distributions leading to a superposition of possible spacetimes. While the superposition part of this is a quantum phenomenon, each spacetime in the superposition is otherwise classical. For example, it is smoothly varying without discrete quantized states. Alternatively, we could say that there's just one spacetime which is somehow uniquely defined by the superposition of all of those mass-energy distributions, as though the effect of matter on the fabric of spacetime is determined by every possible configuration that quantum matter might be in. Both of these approaches are problematic. Let's start with the second one that I described, a singular spacetime shaped by the quantum superposition of mass and energy that it contains. In fact, this is historically the most successful approach to introducing quantum mechanics into general relativity. It's called semi-classical gravity, and it's how Stephen Hawking figured out that radiation leaks out of black holes. The idea is that spacetime curvature is defined by something called the expectation value of the stress energy tensor. Now, the expectation value is just the average measurement value that you would get if you were to measure a quantum system multiple times. It better reflects the global wave function than does a single random measurement or realization of it. In our example of the Earth, we saw that the location of the center of mass doesn't depend on the quantum uncertainty of its component atoms. That's basically the same as saying that its classical stress energy tensor is equal to the expectation value of the total quantum stress energy tensor of all of its atoms. But consider a truly quantum object, say a quantum version of the Earth, that really could exist in a superposition in which there are two locations for its center of mass. If you were to measure the location of the quantum Earth, it would resolve as, say, left or right. The expectation value of its location prior to that measurement would be halfway in between. In semi-classical gravity, that in-between location defines the singular space-time geometry and defines the gravitational field. In regular classical gravity, objects like apples fall towards the center of mass. In semi-classical gravity, apples fall towards the expectation value of the center of mass. In the case of a quantum Earth in superposition, it falls halfway between our two possible locations. In fact, each version of the Earth itself should also fall towards that in-between point. For those living in one of those superpositions, unable to see the other superposition, the Earth would appear to be attracted towards nothing. Needless to say, this seems odd. Semi-classical gravity was always meant to be an approximation, valid only in specific circumstances, but this thought experiment rules it out as a consistent unification of quantum mechanics and classical general relativity. Okay, moving right along. The other option I mentioned for gravity being classical-ish is for there to be a different classical spacetime corresponding to each possible mass-energy distribution in our quantum stress-energy tensor. If our quantum Earth is in a superposition of two locations, then instead of having a single classical spacetime geometry representing the average of the two, we might have a superposition of two spacetime geometries, one for each of the two mass-energy distributions. In this case, our falling apple wouldn't fall towards the average center of mass. Instead, it would fall to one or the other possible locations randomly. This sounds more promising because now we have apparent random motion under gravity that tracks the quantum randomness in the position of the source of that gravity. But there's actually a big problem here also. This time we violate a sacred tenet of quantum mechanics, Heisenberg's uncertainty principle. The argument is due to Feynman, Aronoff, and Rohrlich, and in somewhat simplified form goes like this. We run a good old-fashioned double-slit experiment. A beam of quantum particles is shot at a pair of slits. The quantum properties of the matter allow each particle to be in a superposition of paths passing through both slits at the same time. The wave functions of the particles interfere with themselves and produce an interference pattern on the screen placed after the slits. The shape of the interference pattern tells us the wavelength of the particle's wave function, which is equivalent to knowing its momentum. But according to Heisenberg's uncertainty principle, this means we should not be able to determine the particle position. So, if we measure the interference pattern, we can't know which slit the particle went through. But what if we try to cheat by placing a test mass between the slits? When our quantum particle passes through one or the other of the slits, then it'll exert a gravitational pull on the test particle towards that slit. So the response of the test mass should identify which slit was traversed without disturbing the interference pattern, allowing us to simultaneously measure both position and momentum. This method of cheating Heisenberg only works if the gravitational field of the particle is localized and classical, i.e., the field really does have to pass through one slit or the other, and this has been taken as a solid argument for why gravity can't be truly classical, even if it's allowed to be in superposition. So far, so bad. We found that a singular classical space-time geometry that depends on the collective quantum state of its contents doesn't behave sensibly for quantum superpositions of matter. But an otherwise classical space-time geometry that is in superposition along with the superposition of its contents will betray information about its contents in a way that violates the uncertainty principle. But there is a way to have a singular classical spacetime that allows its quantum contents to still behave like quantum objects. The trick is to add noise, to add a type of randomness to gravity itself. In Jonathan Oppenheim's theory, which he calls post-quantum gravity, we still have a singular spacetime, one gravitational field, but now it fluctuates randomly at every point, and the distribution of values of those fluctuations reflects the quantum superposition of the matter generating that field. Another way to think of it is like this. In regular general relativity, when two objects interact gravitationally, they sort of learn each other's location based on the direction of the gravitational field. It's that perfect learning of position that can violate the uncertainty principle. But in post-quantum gravity, gravitationally interacting objects don't learn precise positions, but rather a probabilistic distribution of the possible positions that depend on the position wave function of the sources of that gravity. Let's see how this works with the example of the quantum Earth in superposition. The apple starts falling generally towards the Earth, but due to the fluctuations in the gravitational field, you can't at first tell whether it's falling more left or more right. In fact, those fluctuations cause the apple to take a sort of random walk, sometimes drawn more to the left superposition, sometimes more to the right. Let's see what the Earth is doing as the apple falls. Well, in Oppenheim's theory, there's feedback between the noisiness of the gravitational field and the quantum matter that generates that field. So the quantum matter of the Earth gets its own random fluctuations. These fluctuations slowly destroy the superposition. They cause decoherence. Basically, they collapse the wave function of the quantum Earth. This causes the Earth to end up at a single location. In a sense, with every interaction between the apple and the Earth's gravitational field, the apple conducts a very gentle measurement of the Earth's position. The strength of these measurements increases as the apple gets closer to the Earth. Over the fall, Earth and apple become correlated, and the Earth's position becomes defined. If the apple fell more to the left, that's where the Earth's center of mass will end up. If to the right, then the right. This fundamental randomness also resolves the issue with the uncertainty principle when we try to use gravity to measure the path in the double-slit experiment. If the gravitational field of a particle traveling through the slits is itself noisy, then that noisiness destroys the information about which path the particle traveled, and we can no longer use the field to identify that path. Perhaps the most radical aspect of Oppenheim's idea is that it throws away determinism. It requires that this noise in the gravitational field is truly random. And perhaps the most radical consequence of that is that it allows for the destruction of quantum information. Conservation of quantum information is thought by many to be among the most fundamental underpinnings of quantum mechanics, that without it, quantum mechanics is inconsistent. At the same time, insisting on the preservation of information led to various challenges like the black hole information paradox. If you allow quantum information to be destroyed by quantum fluctuations, then no such paradox exists. So, it seems Oppenheim's theory can describe in a consistent way how classical spacetime evolves with superpositions of quantum matter, and also how quantum matter itself evolves under the interaction with a classical spacetime. Post-quantum gravity isn't likely to be our final theory, and it may or may not be on the right track, but it's very interesting to see that there are still new directions to solving this century-old problem. It gives us hope that we'll eventually unify our two great theories. Will it be quantum or post-quantum gravity? As long as we figure it out, I'm cool living in either a quantized or a random space-time.